Hello gang. In this chapter we're going to look at single area OSPF, which is a specific type of routing. We'll talk about the characteristics of OSPF. Remember, OSPF is open shortest path first. We'll talk about single area OS2 and OS3. After you finish this chapter, you ought to be able to explain the process by which a link state router learns about other networks. We'll talk about the Cisco iOS routers, how we set them up to do this. We'll show how to configure one. After we do this, I strongly encourage you guys to go into Packet Tracer, build you a little network with 4 or 5 routers in it, and put OSPF on it. Make sure you really understand it and you can make them route between each other's. So here we show that OSPF2 has been around since '88. OSPF3 in '89, but it was updated in 2008. Some of the features of OSPF: it's classless, it's efficient, it's fairly fast to converge, it's extremely scalable, and it's relatively secure, and you'll see why here in a minute. Your OSPF data structures are a little different than some of the others. Your database contains an adjacency database that has basically the neighbor table. It lists all the neighbors that it knows. Then your LSDB, your LSD database, which is your topology table. Finally, the last database used in OSPF is a forwarding database, and that is your routing table. And you can view that with your show IP route. So OSPF routers exchange packets, and those are used to discover neighboring routers and to exchange information about those routers across your network. So here we've got an example, and what we do is we exchange what are called hello packets. And every router using OSPF will exchange a hello packet with every other router directly connected to it. It attempts to establish who these neighbors are with these packets. So these routers also exchange LSAs, and these are the link state information. Routers flood the LSAs to all their adjacent neighbors. The adjacent neighbors receive the LSAs and immediately flood the LSA to other directly connected neighbors until all have received all LSAs. So when one router updates, it's going to send that out to everybody by sending it to its closest routers, who will send it to their closest routers, and so forth. So in this case, router 1 builds the SPF tree that gets ready to be sent out. It's built the topology table received on based on the LSAs. The database will eventually hold all of the information about the entire network, and then it executes its SPF algorithm. From the SPF tree, the best paths are inserted into the routing table. Here we got single area showing that area 0 is called the backbone. Single area OSPF is useful in smaller networks with few routers. Down here we're going to look at multi-area OSPF. And this is a 2-layer hierarchy where all areas must connect to the backbone area. So we have area, here 51 they called it, connected to area 0, our backbone. So a link failure affects a local area only. The ABR, which in this case is router 2, isolates the fault into that area. So in this case, the other routers in area 0 and 1, they don't need to know that the link changed in area 51. These backbone routers that they've listed as R1 and R2 are where it's going to stop. Every router in 51 needs to know that this link went down between these 2 routers. But over here it doesn't matter. Let's say a router in area 1 needs to send something to 51. Well, it's going to ultimately get it to this router 2 and then send it and let them deal with it. It's not going to care what's going on inside that autonomous area. So OSPF messages have to be encapsulated to be sent out. And they start with a data link frame header, an IP packet, then an OSPF packet header, and then my actual information from my OSPF database. So the types of packets that we have, there are basically 5 types. We've got a hello, which is essentially like a ping. It's used to discover the neighbors. A DVD or database description checks for the synchronization. The link state request, which will request information on the link state from router to router. An LSU, which is a link state update, which requests specific update information from those neighbors. And then a link state acknowledgement, or what they call an LSAC, that acknowledges the other packet types. So basically, we send a hello, we get an acknowledgement. We send a database description, we're going to get an acknowledgement. The first type, again, is the hello packet. And that hello packet's going to go out to discover these neighbors. It's going to advertise the perimeter on which the 2 routers must agree to become neighbors. It's going to elect a designated router and a backup designated router on multi-access networks like Ethernet and frame relay. And we'll talk about those in just a minute. So here we've got just a breakdown of the anatomy of that hello packet. I've got my data link frame and then my IP packet frame header, and then the actual OSPF packet header and the OSPF data. At first, we're going to have the version, then we're going to have a type, a packet link, then an area, and a router ID. We're going to have checksum. These 2 are important. This authentication, that's how we get some security included in this. We're going to have our network mask, a hello interval. Then we're going to have the designated router, the backup router, and the list of neighbors. So OSPF hello packets are all transmitted on 224.0.0.5 on IP4 in multicast. And in IP6, they're sent on FF02::5. They're sent every 10 seconds and every 30 seconds on non-broadcast networks. The dead interval is the period that the router waits to receive the packet. So that's while we're waiting to get it back. The router floods the LSDB with information about down neighbors once it knows a network is down. Cisco's default is 4 times the original hello interval. So here we're looking at a link state update. Again, that's our type. That's a type 4 packet. The LSU contains 1 or more LSAs, and LSAs contain route information for the destination networks. When an OSPF router is initially connected to a network, it's going to try to do the following things. It's going to create adjacencies with its neighbors. It's going to exchange routing information and calculate the best routes. It's going to try to reach convergence, and OSPF progresses through several states while trying to get to convergence. So here we're showing just the neighbor adjacencies. And then finally the election of the DR and the BDR. And remember, that only occurs on multi-access networks such as Ethernet. So here we're seeing that we have an adjacency with all of our neighbors. It's interesting, I'd like to point out that they showed a switch in the middle of this, and the reason for that is these switches at layer 3 can do routing. So we have adjacency established with everyone in the network. So first, we have to determine what router is going to become the master. And you can force that by setting the router ID. The highest router ID becomes the master. And then it prepares the packet to go out for the backup. Here they're just showing how it exchanges information. Here's a summary of the link change. You're going to get acknowledgement, thanks. Here's a summary of mine, and then the router 2 is going to send an acknowledgement back that it received the packet. So to enter the router OSPF configuration mode, we're going to do a router OSPF space 10 command. I'm glad they put this on here because this is something that I haven't told y'all before, but y'all need to really be aware of. Use the question mark in Cisco as much as you want because it will show you some of the commands that you might not remember. It'll give you the details on them and tell you a little bit about them. Sometimes just this little bit of reminding is all you need to remember what you're working on. So your router IDs, here they're showing those. Router ID order of precedence. Is it explicitly configured? Yes or no? If yes, use it. If no, is the loopback configured? Yes or no? If it is, then use that. If no, use the highest active configured IP address. There just really wasn't a rule for this, so that's what was chosen. If all your routers on a network are the exact same type and model, you really don't care which one is your backup and which one's your primary. But maybe you've got a network where it is a larger network. You've got one or two devices that are newer and have a higher CPU. In that case, you may want to use those as your primary. So you set that ID by explicitly configuring it, and you can force it. So here again, we're going to assign interfaces to the OSPF area. So we're going to have our network, then we're going to have our areas that it's assigned to. By default, OSPF messages are forwarded out all interfaces. However, these only need to be sent out interfaces connecting to other OSPF routers. So you can turn that off. Turning it off helps with the inefficient use of bandwidth and resources. And it helps with security risk because you know your router advertisements aren't going out anywhere they shouldn't be going out. So the passive interface feature is what helps you do that. Here we see we're doing a passive interface. That's going to prevent the transmission of routing messages through that. But it'll still allow the network to be advertised to other routers. So here we're saying don't send routing information out fast gigabit Ethernet 00. So here we've got how to compute the cost. And in OSPF, the cost is the reference bandwidth divided by the interface bandwidth. So here, for example, I had a 10 meg on 100 meg, I'll get a cost of 1. Or 10 gig, sorry. A 1 gig, I'll get a cost of 1. A fast Ethernet, a 1. Ethernet 10, serial 64, slow serial 1562. The cost of an OSPF route is the accumulated value from one router to the destination network. So here they're doing a show IP route and they only want to include one route. To make it smaller, they're only going to say 172.16.20, that network. So here we see the cost, 65. Route metrics is 65. Traffic share count is 1. So you can use the command AutoCost reference bandwidth to have it automatically figure this for you. This must be configured on every router in the OSPF domain. Notice that the value is expressed in megabits per second. So gigabit, the auto reference is 1,000. 10 gigabit, it would be 10,000. On Cisco routers, the default bandwidth on most serial interfaces is 1.544. So we're basically set to just above a T1 here. And here they're showing that I can adjust that. Both the bandwidth interface and the the IP OSPF cost command achieve the same result, which is to provide an accurate value for determining our best route. And here I'm able to see that adjacency has been formed with my neighbors. The state full tells me that. So looking at show IP protocols now shows me outgoing update filter for all interfaces is not set, but the router ID is set and the number of areas in this router is set. Here we can just verify that. So here we're looking at a show OSPF interface brief to show me what our costs are on networks out our various interfaces. And here they want to show that you can run multiple protocols. For example, router 1 and 2 can run OSPF 2 and 3 together so that each will have its own table of 4 and 6 addresses. This is actually pretty common right now, as very, very little of the internet is just pure 6 because so many people are still running 4. So here we've got our similarities between our links. 2 and 3, they're both link state. They use the routing algorithm of SPF. The metric is cost. They support the 2-level hierarchy areas. They send the same types of packets. The router ID is a 32-bit ID. The DR and the BDR are decided by an election process based on the router ID. Here's where they get a little different. 2 and 3, 2 is an IP4, 3 is an IP6. 2 is an IP4 source and 3 is a 6. Their choices of how to broadcast those are different also because we're going to use multicast 224.0.0.5 in V2. And we're going to use FF02::5 in 3 because, again, we're using IP6 addresses. The command to view is a little different as well, as you see here. OSPF2 has plain text as the only way to authenticate. OSPF3 uses the auto built-in encryption of IP6 to encrypt data so that it's more secure. So here we got an example showing how linked local addresses are sent with OSPF3. And again here, turn it on, IP6 unicast routing. Go to your interface, in this case, interface G00. Description they added, then assign it an IP. Do a no shutdown. Again, second interface here is serial. We assign it an IP, but we have to give a clock rate because it's serial and a no shutdown. So in dealing with OSPF3, step 1, enable unicast routing. Step 2, configure a link local address. Configure a 32-bit router ID. Configure the optional routing specifics, such as the bandwidth, if you need to change it from that default. And then enable IP6 routing by issuing the IPv6 OSPF area command. So here we're just looking with show IP6 interface brief, give you an idea of what it looks like. Link local addresses are automatically created when an IP6 global unicast address is assigned to the interface. Global unicast addresses are not required. Cisco routers create the link local address using FE80::10 prefix. This is how we get our IP addresses. I don't know how familiar you guys are with IP6. I know it's a little new. But when you're assigned a 6 address from like an ISP, like Comcast or whatever, what you find out is that you get an entire class of addresses, and then it's up to you to assign those individual addresses to devices on your network. Here we're assigning that link local. It can be manually configured, which gives you the ability to create an address that's easy to remember. Here's the process of creating the router ID. Again, is it explicitly configured? Then use it. Is loopback configured? Yes, use that. If no, what is the highest IP address? finally, if no interface has IP trying to configure OSPF3, then we're going to get an error. And here we're seeing that we're assigning router 1 to that area, router ID 1.1.1.1. We can modify that ID by just changing it by IPv6 router OSPF10 router ID. I left it 1. I could put 1.2.2.2. Instead of using the network router configuration mode command to specify matching interfaces, OSPF3 is configured directly on the interface. So see here, it just looks a little different. And here we'll do a show IP6 OSPF interface brief. It'll show me the network connected and the cost metrics associated. And there's our routing table. So that's a quick rundown of OSPF. Basically, IP4 uses V2, 6 uses 3. They're classless. They have a default administrative distance of 110, which is denoted in the routing table with a source code of an O. OSPF2 is enabled with the router OSPF process ID. The network command uses a wildcard mask instead of a subnet mask. Now remember from your reading, your wildcard mask is exactly the opposite. In a Class C network, if I have a subnet mask of 255.255.255.0, a wildcard is 0.0.0.255. So make sure you remember that. That's one of the common mistakes when people set this up for the first time. And I would like to tell you I haven't done it, but I've done it quite a bit. I'll put in the subnet mask instead of the wildcard. And Cisco assumes you know what you're doing, so it lets you do it. It assumes that you mean this is going to be a really small network, not a Class C. A really large network. By default, OSPF hello packets are sent every 10 seconds on multi-access segments and 30 on your frame relay ATM segments. You can change that. The dead interval is 4 times the hello by default. For routers to become adjacent, their hello interval, dead interval, and network types must all match. In a multi-access network, you need a DR and a BDR, and those are going to be elected based on the router ID that you either set or that is automatically maintained. In multi-access networks, the router with the highest ID is the DR, second highest is the BDR. We're not going to get into it here, but you can have more than one BDR, and we'll talk about that, I think, next week. Show IP protocols is going to verify that information. OSPF3 is enabled on an interface and not under router configuration mode. It needs a link local address to be configured. Show IP protocols is going to use to be verifying the information. And show IP6 protocols will give you the V3 information. And that is a quick rundown on Chapter 8.